I don't know why it does that. Thank you so much. Oh, for crying out loud. It keeps not remembering. Right, I need to think about that. Appreciate it, Kick. Yeah, I don't know what was going on there. But anyway, I guess that's all fine. Um, yeah, thank you, thank you, thank you. How are you guys doing? Right. So I guess I'll just start again. So in today's stream, we're going to be doing the tile-based renderer. So we'll go over again what that is, what the different approaches are, and um, we'll talk about the stuff we did last stream. But last stream, I kind of took a lot longer than I expected. So I didn't really bother uploading that video because it was kind of long and there was lots of mistakes throughout the whole thing. So I just decided to if I just redo the recap of this stream, then I'll just recap what we did last stream. Yeah, sorry, if I redo the explanation this stream, then I'll recap what we ended up doing last stream and where we got stuck. And then we can carry on and hopefully get it all working today. So, you know, the main goal of this game is just to render a ton of ellipsoids. They're not going to be ultra small, they're going to be kind of nicely sized. We will see them. But I want to have this part of it be fast because this is the main rendering. And currently we ray trace per pixel. So we do a full screen launch of rays in a compute shader and we ray trace every single ellipsoid. So right now there's only one. And that's because inside the ray tracing shader, there is just a hard-coded array. So this will eventually come from a buffer. Be uploaded from the CPU every frame. Here's all the ellipsoids I want to render. Well, okay, it'll work a bit differently than that when we add models and model instances. So we want to make sure that this list is as small as possible for each pixel, because the longer this list is, the more ray versus ellipsoid intersections that will need to happen, and obviously some more work other than just that. So essentially the tile-based renderer is like an acceleration structure. So you're essentially accelerating the ray tracing through this acceleration structure. You could use BVHs, right? Those will work in world space. They'll work in any space really. BVHs are quite good. You can shoot rays from any direction. But on GPUs, GPUs just work better with arrays, obviously, than a tree. So one approach you can take. So we're still going to have some sort of other acceleration structure for when we do GI, but this is one which is hyper optimized around shooting rays from the camera. So yeah, that's its downside. So effectively, rather than making an array of ellipsoids per pixel, you instead make an array, a rough guess of what is going to be hit for a group of pixels, and that group of pixels is a tile. If I can, there we go, trigger that. So these are what the tiles are going to look like. They're kind of like 16 by 16 pixels, but we could probably make it 32 by 32 on a 4K screen. We've got to play around with that. So effectively what we are going to be doing is taking an ellipsoid, and we've got to get the bounding box for it in screen space and basically add it to each array inside each tile. So the smaller the tiles are, the more tiles you have. And obviously the more tiles you have, the more duplicates of the same ellipsoid get placed into memory. So there is a bit of a balance on those things. But the larger the tile is, the more pixels that share the same tile, and so that means the more ellipsoids are going to be in that tile, which some pixels in that tile will inherently miss. So you just have to be careful about that. So yeah, it's a bit of a bit of a trade-off, really. You just got to measure it. But yeah, so we'll go over the 3 different strategies on how you can bin ellipsoids in a multi-threaded way. So you always need the screen bounding box, basically. So the main problem is you want to basically make an array per tile, and you don't necessarily know up front what the size of that array is going to be. So it can be quite a difficult problem to solve. So there's a few ways you can solve it, and that is you can iterate over. If you take the bounding box, in a compute shader, you get 1 thread per ellipsoid, and you basically get the bounding box, and you do a for loop over the columns and the rows, and essentially you just add an atomic counter to each tile. So you increment it by 1, and that's your insert index into the array, and you insert it, right? But that will only work if you fix allocated your arrays and you stop inserting when you reach a maximum, which then leads to another problem if you take that approach, and that is the arrays. This was my train of thought now. So yeah, if they're fixed allocated, the compute shaders, they don't always execute deterministic in the same way every single frame, right? You'll get some ellipsoids which get inserted before others in different frames. So yeah, so the compute shaders will execute threads in different orders, essentially. So thread groups and threads can execute in different orders. Wait, sorry. It's thread groups because every wave executes in lockstep. So essentially you could get one group of 32 ellipsoids that could just be inserted before or after another group, and it changes every single frame. So that would mean if you have this fixed sized array and you overflow that fixed sized array, you'll get flickering because some frames, some ellipsoids will be inserted, and other frames, other ones will be inserted. So the way you could solve it is you do 2 passes, and you go over it. So each thread gets an ellipsoid, and it goes over, the screen bounds that it takes up, and inserts into every single tile, right? Sorry. Instead of inserting into every single tile, it increments a counter. And then after you've done that for every single ellipsoid, you could then run another shader which goes over all of the tiles and then sub-allocates these arrays which have their sizes will be much different, right? And you'll sub-allocate from one large buffer each sub-array. But then that approach means you've got 2 passes. And it's quite inefficient. And also there's another problem with that approach is, say if you have multiple ellipsoids over the same area on the screen, you're doing an atomic increment. And the atomic increment will be costly if you have two ellipsoids on different compute units adding to that atomic counter. They're going to have to wait for one another and stop and synchronize some memory so that they can increment the atomic counter fairly. So yeah, those are the problems with that approach. You can take a different approach, which is what the UI system currently uses, and this is what we're using to debug draw this, is you could, instead of going over every single ellipsoid, you can instead go over every single tile, and one thread gets a tile in a compute shader, and then you go over every single ellipsoid within that thread. You just do another for loop in the compute shader. But yeah, the problem with this approach is it doesn't scale. When the ellipsoid list gets very big, you're having groups of threads going over the same massive array of ellipsoids, and it can get quite costly. But the benefit of this approach is that within the same compute shader at the top, you can literally just write a little counter, a little count, and you could go over the whole array the first time and see which ellipsoids overlap your pixel, and then you allocate the array, and then you do another pass where you go over it all again and actually fit them in the array. But again, that's a 2-pass system, and it kind of sucks. So there is a third way on how you can do it, and this is the approach we'll be taking and actually took in the past. And that is effectively there is one more requirement that I did not go over. And the other requirement is that our ellipsoids need to be sorted from front to back, so that we ray trace front to back, and we can just assume that that is the way it is, and then we can alpha blend properly. So the problem with the other two approaches is you have to have a separate pass, which then sorts the ellipsoids. So the third approach is to essentially do it all in one go. So you can imagine you have 16 bits, which stores the tile index, and then you have a further 16 bits, which stores probably the depth. So you sort all of your ellipsoids by this, and because the tile index is in the most significant bits, it will sort by the tile index first, and then by the depth. Meaning that if you sorted a whole array, it will do it all in one sort pass. But the sort pass might take many compute passes depending on the algorithm. And then you end up with a whole array sorted by tiles and depth, and you don't have that problem where each tile has a different sized array of ellipsoids. Now the problem with this approach is that you've just sorted the array, so you don't know where each tile index starts. So you need to do one more pass over the sort keys, which what these are called. This is a sort key. And you need to basically check, you need to find the boundary between one tile and another tile. And you can use that to figure out, hey, this is where this tile starts, basically. And then there is another parallel array, which is called the payload. This is the payload, and we'll be using it. It's another E32. It'll be the ellipsoid index. So we'll sort, the sorting algorithm that we're using supports having a sort key of 32 bits, and it allows us to also have an accompanying payload buffer alongside it, which gets sorted with it. So essentially you can sort a 64-bit number, but it's in two different buffers. So we're using the AMD parallel sort. It's free and open source. You can go and implement it in your game. I poured it from, it's in HLSL or GLSL. They have some macros that they handle both, but I ported it over to my custom shader compiler. But yeah, that's about the recap there for how we're going to do it. Has anyone got any questions about what we just said? So while I'm waiting for those questions, if there are any, I'll go over what we did last stream and where we got stuck and what was the problem. So effectively, we just started off by having making some new buffers. We're calling these the binned ellipsoids. So these hold the actual ellipsoid structures. So these are in graphics shared, the generated one in it. Yeah. So it's got binned ellipsoid, it's got transform, wild from ellipsoid, a material index, and an alpha. It's not really packed yet. I want to make it all unpacked data so we can pack it all down and really see the numbers come down and to see how much of a benefit we get from actually packing stuff. And yeah, just see some numbers. It's always good to see numbers and test things so you get more of an intuition for how good you can make things up front if you think about, how good you can make things if you think about some of these things up front. I've got the sort keys array, which has those sort keys in it, and then the sort payload. We need to make a compute shader which will fill in which will fill in these two arrays. So I just made the code which initializes those buffers. Initializes these buffers here when we start up the game. Just some buffers. These are obviously the binned ellipsoid, and these are obviously U32s. Then, every frame, we're just uploading the array which we had in the shader. We're just doing it from the CPU side now this time. And we'll make it I'll make it better later, obviously. Right, so where did we get to last stream? So last stream, it was basically the focus of what I ended up kind of focusing on was getting an axis line bounding box for the ellipsoid, moving that into screen space and get a 2D bounding box, and so we can obviously see which tiles we go over. Now, I encountered some issues. I think a couple of issues got me stuck. So we didn't really get too far on that. So I'll go over what we have here. This is just test code. We're not doing it in this ray tracing shader. I'm just doing it so I can visualize like the actual results of the code by drawing debug stuff, and it's just easier doing it here. And then I'll simplify it and then bring it into a separate shader where it actually does the work. So the first problem I had is like, how do I get the how do I take a local space box? So I'll just make this around the ellipsoid. It's quite easy, right? Just get the ellipsoid half dims and then that's the box. How do I get a view space aligned axis line bounding box? And then how do I Yeah, that was the main idea. Um, but the thing that I was doing is taking the half dimensions vector and the center position and only translating that. And then that made it so that as I would translate these into view space, and then I would basically get the mirror. You can already see the problem from here. I would mirror the x, or mirror the x of the vector, take the min and max of these coordinates that it's pointing to. And if you mirror the x, you'll do something like that, right? So when I would look at it at a bit of a funny angle, we would get a very thin bounding box instead of how it should look, this bounding box. So the thing I was missing, and I have done this in the past, I just forgot about it, is we actually need to transform from the local space of the ellipsoid is 3 basis vectors. So the basis vectors obviously go down x, y, and z. And then you translate these into view space. And then you can use these basis vectors to compute the view space bounding box by flipping them and taking the min and max of every single point. This is not to scale, so it doesn't look like it works, but it works. And that's probably the reason why I was having problems, because drawings are not to scale. So you take all those points to min and max, and that'd be your bounding box in view space. Obviously, I've not done it to scale, but something like that. So that was the first problem I had, and we solved that. Oh, wait. Yeah. There was a nice little simple function we made. So it just takes that x from local, so that maybe goes to view space from local, and takes the basis vectors of that transform, multiplies it with the half dims of the ellipsoid, and then so this would do the scale and rotate. Oh wait, will it? Yeah, just a scale and rotate. Basically, it projects the half dims across those axes, and then essentially we just take a max here. Yeah, we ABS it and take a max of everything. This saves flipping it. So then the next thing we had to do was get it from view space into screen space. And this is where I got a bit confused of like with the projection matrix. I was like, right, I need a projection matrix. So I fished one off the internet, and I forgot that the projection matrix doesn't do the divide by Z. So in the past I've just done this, like I don't need a projection matrix. I've never needed one. In the past I've just done the maths myself by dividing by Z. You know, just doing it all without a matrix. But I thought, let me try and do this transform from local space all the way into screen space in one single matrix multiplier. But obviously that's not possible. Because the projection matrix doesn't get you. It's in. So you go from. It doesn't get you into this sort of like -1 to 1 space. It's NDC, it's called normalized device coordinates. It doesn't get you in there alone. It gets you pretty close. It gets you there, and then you got to divide by Z. it gets you to the part before you divide by z, and that snaps it into this box. So what it ends up doing is taking the values and scaling them such that this is the far plane and this is the near plane, and scaling the values that you transform such that if you was to have a z which goes past 120, it actually will sit outside this box, and if it goes less than 30, it will go before the box, and therefore it's outside the bounds of the normalized device coordinates. So yeah, I was just confusing the projection matrix with it getting into normalized device coordinate space, but it doesn't actually do that, obviously. That is done after the vertex shader. And from the vertex shader, typically you set something like GL position. If you do GLSL, right, you will do your projection matrix times, your view matrix times model times the vertex, right, in local space of the model, or whichever way around you do it. And this ultimately just sets, so in GLSL talk, it sets your X, Y, Z, and then essentially your Z ends up going here because of the projection matrix. It puts something in the fourth row or column, whichever one it is, which basically says which like a 1 or a -1 depending on how you do it, and it will like copy the final Z component to the W column, and then after the vertex shader is ran, the driver is going to do this for you. So that will then snap it all into normalized device coordinate space, which is -1 to 1, including the Z. But the W is going to stay at, the W will stay as the original Z value. And they do this because, I forgot the reason why they do it. It's so it could be passed to, it might be because it could be passed to the pixel shader. I completely forget. But yeah, so that's the bit I was missing, right? The projection matrix doesn't do this, that part of it. So that's what I was researching the end of last stream. So now that I know that, we don't need this projection matrix code anymore. We just will carry on with a manual way of doing it. So I think what I'd like to do, we'll still need to get into view space from local space. So ooh. What do we need to generate the transform out to ABB? We're going to need the axis vectors, right? So maybe I just make another function which takes in the axis vectors. So yeah, why do I need this? Because I've, in the ellipsoid, I have the world from local transform, right? So this, let's have a look. Binned ellipsoid. Right, maybe this binned ellipsoid could actually contain the view. We could already pre-multiply it in a previous... Oh, no, I don't think we can pre-multiply it. Wait. Can we? So, we'll have multiple models. When the model has been like... Yeah, when the model tries to bin... Wait, what do we need? No, this one is a world from ellipsoid because it ray traces in world space. Right, but we will have the view from local. We'll have one matrix which takes us into the local space of the model from the ellipsoid, and then to the right. I think we need to. What's the code like to combine two matrices again? It's quite a lot, isn't it? But yeah. So essentially, I need to do this, but without that, I probably wouldn't need the translation at that point. Oh no, I need both, isn't it? Yeah. Right, yeah, so I end up just combining it like this in the end. Right, okay, it's good. So, we don't need this projection thing. What is this? Yeah, so we don't need all these extra functions actually. Let's go back to the shared one. We'll still call it dims though, it gets you the dimensions. Or the half dims. Alright. So we can debug draw what we have so far. I guess let's try that. So I think we've got a red bounding box. And then we had like a, yeah. So this just shows you the view space aligned version of where's the scheme for no need screen for projection. What? I could just hand roll the maths manually rather than doing a whole damn matrix for it. Yeah, we're not doing that anymore. Right. Hmm. 4-3. Oh, okay, get rid of that. Okay, so right now, oh, I forgot which one did we forget? Right, these are the screen space ones. We'll do these in a bit. So yeah, I think it's gonna be actually be white. The view space box. I think the local space one was red. So we're transforming the ellipsoid that was rendering, and we're just putting a bounding box around it in local space, and then we're transforming it into view space and taking the larger box around it. So these two spheres that you're seeing on the corners, these are the important corners. So these ones define the box in screen space. If we take the outer, if you map these into screen space and take the outer box between these, that'll be the box we use in screen space. And you'll notice when I go across the halfway point, it will flip over like that, right? Now, something I ought to be careful about is this. Actually. Yeah, I might look at some of my previous code because I've got that access to that now and solve that problem, because right here we did that same thing. You're not gonna... You kind of want to select this corner here and put the box from... Well, no, you probably want a third one actually. Yeah, I think that's the way I solved it in the past, I reckon. Probably took 3 points back. So I think in the Discord I put down the exact thing that we want to do. Welcome. Here's the list. Yeah, so we take the basis vectors x, y, z, basis vectors from local space into world space. Yeah, okay, it's going to be a bit different from this. So we're going to take it from local space all the way to view space. And then we will divide by z. Something like that. Yeah, you know what, I'm just going to look at the old code. Past me is confusing present me. So we did this in the past. So here's the old shader. Old graphics code. There is some shader code too we'll probably look at. So in here there's a... I think it's just called tile binning. Not the UI one though. Sphere tile binning. Here it is. Oh, then I do some hack this time. Yeah, I think I did some hack. Bit of a rough guess, and it worked out better. Alright, so maybe we cannot trust this code, but we can trust how it gets into screen space though. The near clip space, so divide by Z from view space, right? Camera origin. Takes the min-max point. Alright, let's take this code and we might make it into a function. So we can say, go from view to screen or something like this. Well, we could say, see if we can make it. Transform screen from view. Yeah. So you would pass in your actual view space, position of view space. And we probably want information about We'll figure it out. Yeah, pixel size at new clip. There might be some structure where we can pass in that has information about the specific view, but maybe we just need a single field. So how big is the pixel size in new clip plane? So if you divide by Z, we'll get the position at near clip space. Then we'll get the then we'll divide it again. I don't know why I'm doing it. I could do it a different way. So divide S. Position view space dot xy divided by position view space dot z. Then we'll do this. Take the new clip space, put another divide by this. We could probably pass in the inverse of that and just do a multiply, but there we go. So that should get you in screen space. Wait, we need an offset. Where's the offset? Then we offset by the screen. So we already have this as a global. But maybe you should pass it in. So this would just be the scene. Yeah, we'll pass it in. So screen dims, half of that. We could do E32, it doesn't matter. Now we do float, first float. So you just add yeah. So I guess I could draw it out. So essentially, you've got this point in view space. This is the view frustum. And you're looking through it. You divide it by Z. So it goes from being here down to the unit distance away, right? So it'll be end up being here. Divide the X and Y coordinate by Z. And then so I get you the new clip space. It's just 2D vector. Then you're getting the pixel size at the new clip plane. So say if your pixel is like this big, as we're dividing it, it will basically scale it back up to as if it was this kind of resolution. So we'll get it as like a kind of a pixel coordinate. And then because this position is relative from the center of the screen, so this is origin 0, 0 right here, we're basically just offsetting it by a half of the screen dimensions, and therefore bring it into, you know, in my coordinate space, bottom left is origin 0, 0. So it just brings it into that, just offsets it such that it is actually in a screen position now. Cool, so we've got that nice little function we can reuse and that, which would be pretty sweet. So we've got two we need to bring back, and that is the half dims. and the center position. So half dims screen space is equal to this function. So now that's the thing, right? This is a position, and then there's like just a vector. So if you're moving a vector back, can you move vectors back? That's a good point. Oh no, we don't want to move vectors back. We need to get the two most important points. Yeah. Whoopsie. Minimax point. Yeah, I swear I did this in the past. Screen space, like so. Cool, so now they're in screen space, we can plot them. Well, yeah, we can generate the center position screen space. So that is, and you're on the half dims as well, right? Half dims, that'd be something like multiply scalar. Then a subtract. The max and the min. And then you obviously want to divide that by 2, so 0 times by 0.5. Then if we add from the min point of screen space the half dims, we'll end up with a center position, and we can use that to draw a circle to represent a point, and then a little vector. So all in all, I reckon, right, we can not draw this view space box and just draw the screen space one and just see how that looks. And then I'll look at the old code and see how that, see if I can see some of this code in there. Right, we're missing the screen dims, so that is global scene dims F. And the other one is pixel size at near clip plane. Right, let's give that a go. So it's not really a good visualization. We can improve it. But let me... So we're still seeing the two spheres. The two spheres are in view space, and they're representing the two important corners you want to bring back into screen space. This green one and this blue one of the axis line bounding box around the ellipsoid. Then we've got this white circle, which is actually in screen space, and this red line, which is actually in screen space as well. They represent obviously the center position of the, yeah, and the this is the half dims. So what I want instead to do is draw a axis line bounding box and not this silly thing. But it seems to be working apparently. But yeah, I don't think it works fully though. There is a bug that I want to fix. To actually draw it properly, let's do the ABB. Center position, half dims. Now the half dims we did see is actually negative. So what we actually want to do is take the ABS of that. And then that'll just be a bit better. And we'll put a nice little box around it, right? We'll say like, hey, I want a 4-pixel border. So we can hopefully see the ellipsoid on the inside. And I'll just completely cover the ellipsoid when we debug draw this box around it. Right. So that's clearly not looking great. It went like that, was it? What have I done wrong? Oh, the min-max point's not really min-max points. Is that what it is? Yeah, I remember Bob's problem before. Let's take a look at the passcode. I remember solving it by probably changing the Z component manually. Here's the old code. Oh, I hope it's there. Yeah, so this is the one that solved all of the problems. Was this outer screen bounds of 3D ABB? Yeah, so I did use this for the right. So I took the axes. Yeah. What's sine about? Oh yeah, I got the sine. Center position. Yeah, so I take 3 important points instead of 2. Yeah, I remember that one. Center position in view space. Why do I need the closest depth? Oh, I was encoding that into the occlusion buffer. Right, we'll be doing that soonish. No, maybe we won't. We won't need that soonish. Right, what we do have is this. Oh, I did 3 near points, did I? Interesting. Why did I need 3 nears? And a far. And then I did a full min and max on all of that. Bananas. Projector screen space. Yeah, basically it's made another one of those functions. Cool, so let me just debug draw that thing again. Of that view space box and just see like why I picked 3 important corners. Sorry, 4. I think you only need 3. So is it because you can't tell which one it is? So there's one important corner and there's another dark blue one down there. It's quite difficult to see, but there is one there. So because on this side of the screen it takes the near top right and then far bottom left. And then it obviously just mirrors it across the x-axis when it goes over the boundary. And then down there and down. Alright, so it just mirrors them. But the problem is when they reach the center, like this, you're clearly picking the wrong one. So what I think we should just do is just mirror that one, pick the front one. To always pick the... Don't think there's a problem. Oh, I think it's like when you get about middle. Right, technically I haven't gone over the... Alright, this is why. Technically you need to do... Right, projecting those to screen. Then you're taking the min of every point. Yeah, and the max. Like, let's take a screenshot right here. Shoot, I haven't got my UI. Got the tiled debug draw, just drawn over the whole UI. Let's just disable that quick. So in the screenshot view, let's just pop into here and take a little look. I think there's a oh, what I was looking for. Right, I'll do that one again. So I'm thinking, right, that lower left is actually lower than that. So that's why I've picked like a few corners. There's oh, why did I close the damn game? There's cases where you go over the middle of the screen and it's sort of, yeah. As you see, it sort of goes jagged this, downward this way, and then it's kind of like a straight line. So this is definitely lower than this. So actually, we need 2 more points. We need the one down from this important point, near point, and the one right from that point, important point, or actually, yeah, along the X and along the Y, basically, depending on which way around it is. And that's what I was doing with this code, the old code. All right. That's okay. Right. I'm just going to take a quick little break and then we'll copy this over, get that in, and then we'll have the code necessary to get a screen bounding box around the ellipsoid. Then we can do the process of actually trying to emit these into the sorting buffer and call the sort and then start seeing them binned, hopefully. So yeah, I'll be back in a couple of minutes. Meantime, enjoy the tunes. Oh, right. So I need to get those important corners on the view space bounding box. So we actually bring back into screen space instead. So this is some old code. I'm just gonna nick this, and we shall then. Right, thank you, Pass Henry. Right. So important near 0.1, 0.2, 0.3, and far. So this was based on, figure this one out. You see, I reckon we can make a vector for it and I can just whiz all the crap out of it and get the vectors I want. Make the code a bit neater that way. Sine. Right, it takes the sine and multiplies it with. Whereas this one would just do half dims. Yeah. Exactly. So I think what I need to do is make an important vector. Right. Make it a vector 4 instead, so we can just basically have a regular Z, positive Z, and a negated Z. So since we're doing an add, we basically want to use the near one for 3 of them. So I think the way it's going to go. So we take the center position of the box in view space, and we essentially just do some like X, Y, W. Well, we'll do the negative one first, like that. So become X, Y, Z. Oh, wait, we can't do that. Because we need negated. We can just change it out for a subtract. Cool. I'll do it. So positive and negative, that'll work fine like that. This one wants a negated X, but not negated Y. Yeah, I don't know if we're about to do that. Yeah. I'm just trying to make it a bit cleaner, you know? Right, I guess we'll just we'll roll with this again. We'll call it IV. Let's keep it short. So we'll do like an IV.x, then IV.z, but a negate version. Right, so that'll be better. So that's got, yeah, negated x. So it's the near point for the opposite end of the x-axis and the near point opposite end of the y-axis. Then the final one is the far point with negative xy. So we can draw these so we see what they are. Cool, so you get those in view space, those lovely points. Then you chuck them into this function here. We've got a new one. You know, I want to actually make the effort and compute the inverse of this. That would just go the other way around, wouldn't it? Yeah, technically you just divide it the other way around. So here we want to say screen from clip space scale. Yeah, maybe we'll call it that instead. Cool. So if we go into this function here, we'll call it screen from clip space scale. This then becomes a multiply instead of a divide. So it's just the inverse of the previous meaning, but just named a bit nicer for that. Right, so what we actually want is to use this here. Important near the view space, bring it to screen space. We're going to shorthand it. A bit too long otherwise. I change my mind on this all the time. Right, and then we produce the bottom left and the top right. There's this sort of in I need to remove. Bit better. Remove this in. Well, all those actually. Just jam over those. Right, it's a lot less verbose. So you take a min of all those and a max of all of those. So this is in screen space as floating point. Right. So I guess I can just call it min max, but yeah, I'll call it min max here, won't it? Yeah, we'll keep it as float. So max, min. Cool. And then we use those to compute the half dims and the center position, and then I displayed this sort of AABB. So let's take a look at that and see how well it looks now. Confused why. Yeah, right, let's not display that. Now we'll display all these different points, these important points. So we'll do a nice, red, green, and we do cyan. See, blue's terrible. Let's do cyan, and let's do maybe something like magenta. So near 0.1, 2, 3. So these will be at the front of the view space bounding box, and then the far point Ah, I did the view space ones. No worries. Cool. Oh no, I want the view space ones. Yeah. Alright. So this should hopefully be a screen space bounding box. We get to see kind of a little bit what these variables are here visually. Ooh. What are you doing? All right. Then undo that vector 4 thing we tried to do. Do some fancy swizzle trick. Kind of failed. Alright though. Right, an extra bracket than we need. Oh. Only on the top one. So, what's going on here? Alright. Oh, I didn't pass in the graphics global scene dims F. Neat. Exercise the nuclear plane, where you at? Where you at? Oh. I still need that. So I actually use it in the ray tracing code to determine how to do the anti-aliasing in this shader. It's just a little hack. I call it ray trace anti-aliasing to make it sound cool, because it's kind of ray tracing it. Yeah. Right, what's this one complaining about? Redefinition. What? I'm super confused. Ah, Niclip. Oops. What's this one complaining about? There's 3 in there. Not enough arguments. Oh, I got a multiply. Probably make that even less. Neat. Right. So yeah, we're effectively taking the half dims of the view space. There we go. So that was a bit of a rough guess. It's not going to be the best. Right, something's clearly wrong there. We sort that one out. I can't see the far point. Yeah, we'll look into why it's just so painfully bad. Here, especially. But yeah, so all these points are, you can see them here, they're like red, green, magenta, and cyan, and they kind of flip when you go over. They should do. Right, they're not flipping when you go over. It's probably the issue. Oh, that shouldn't be a negative Z, so not getting the other one. So yeah, all we're doing is taking those half dims of the ABB and view space and just essentially offsetting from the center and picking the most important corners to bring back into screen space. Oh, that's a problem. I remember having that one in the past. and then bringing these back into screen space and using that to make this screen space bounding box, which we'll see in here. Definitely a worst case bounding box. It's not perfect. So I just fixed this where the far point was not using the far Z. So we wasn't getting it at the back, one of the back corners of the view space bounding box. So we're getting that now. So you see this green one, technically that's in the right place. You can draw a box around it like that. And that's the front face of the view space bounding box. This is the back left far point of a 3D bounding box aligned to view space. And this is what's helping it be sized properly. Right, that failed. So it's not doing the flipping. It's not flipping the spheres around. Where did that code go? You have to there's the sign, isn't it? There's the sign thing. Where is that? I think I need to copy sign center position. I think that's what we're missing. Yeah, so it flips now. You'll see the red one and green one will swap position when you flip over the X, and then they'll go down to the bottom when it goes past the middle of the screen. Right. So that seems alright now. As you can tell, it's definitely a rough guess. When you get closer to the camera, the less effective it is and the more screen tiles it's going to go in. But the smaller it gets, the less of an error it actually has, which is great. And the closer it is to the center of the screen, the better. But this is the reason why it's so bad on the edges is because we've got a very high field of view, which we're probably not going to have later on in the game anyway. We just got to be very careful to make sure we've got the numbers right. I think we have though. We'll double check. So, as you tell, it's in the dead center of the screen. Oh, yeah. It's growing towards the camera. But why is it causing it to do that? Yes, it's nice and snug there, isn't it? There's a bit of error though, obviously. That's okay. But yeah, so if I was to draw the view space box, what you would see is, imagine drawing a rectangle between these 3 points here. It is moving, so it's a bit difficult. But then that's the front face of the box. And then there's like essentially, maybe I'll take a screenshot. So imagine drawing a rectangle here. This is the front face of the box. Then essentially there's a diagonal line from this corner going down to here. And then there's the right face over here, probably going diagonal like that. And then there's the another face going diagonal like this, around to there like that. So that'll be that view space bounding box. And essentially we're just taking the maximum around that. So we're getting into some area which is obviously not where the ellipsoid is. This is quite a lot of waste. I don't know why it's this bad though. I think that's just the way it is. But we're not having this high field of view in the actual game, so potentially it's going to actually help. I'm just using a high field of view right now. So the code that I write, I'm making sure it doesn't break. I'm making sure the algorithms that I write are not... I can handle this high field of view. But because I've not settled on a particular field of view yet, I should probably do that soon though. Yeah, maybe we should change it. Cool. Right. So now we've got that code, which will allow us to... I think we've got to figure out, like, are we behind the camera? And if so, do not do anything. Let me just double check in the old code. So this is the occlusion culling code, which we're going to be doing at some point. Oh, okay, this was using the occlusion culling. It's just a general function. Yeah, so if it's not in bounds, basically, so I'm taking the center position of the box at the half dims along the Z, and then if it's less than the near clip plane distance, right, gotcha. Cool, we'll make sure we've got that in there as well. So, neat. We'll dump it in here and then we'll actually write the new shader. So it's like if so center position view space, half dims view space, near clip distance. Behind camera. Right, so let's make a new shader. Okay. Drop it in. Think. Ooh, this is a... Alright, let's put it in. So I'm just trying to think ahead to the future because I've got a plan. So in the future I want to have model instances which will go over all of their ellipsoids per thread and try and bin them into screen tiles so produce this sort of render ellipsoid. Yeah. And then you will copy it once into a buffer and then many times into the sort. Yeah. Right. So then what do we call this one for now? We'll just call this bin ellipsoids. Tile bin ellipsoids. UI tile binning, yeah, that's what I called that one. Alright. Cool. So let's make this constant so we pass in. Right, so I want to essentially make a texture buffer. I want to read from a buffer which is of type graphics. Bin ellipsoid, I think I called it in the end. Yeah, bin ellipsoid. So these are the ellipsoids. In the future, we will actually output this array in this shader. But yeah, for now, we're just uploading these from CPU side. We'll add model instances later on. So yeah, we'll change the shader later. Nice. And we want to output the sort keys. Yeah, so U32 sort keys and payload. Cool. So, alrighty, so we're gonna get our bin ellipsoid. Just call it E, I guess. SV dispatch index. Right, and we want to say if this is greater than the number of ellipsoids, then return greater than or equal to. Now, fish out the ellipsoid. Now we don't have the yeah, so we combine these matrices, so it's yeah. I want to produce a view from ellipsoids to be a multiply between a graphics global view from world and then the E world from ellipsoid. So we join those two together and make this one matrix here. Now I want to take that code from the other shader that we used to work this all out. Ray trace anti-aliasing this shader. Here's all that test code. Yoink. Make sure we get back to where we were. Right, so here's all that super lovely code. So view from ellipsoid. See, the word local is a bit ambiguous already because it could be the local space of the model or local space of an actual ellipsoid. So I should not really be using the word local anymore. Not really a good name. So, rightio. So we then take a unit sphere or ellipsoid in our case, you know, three axes of radius, right through this, you know, so that will be the bounding box in the local space of the Yeah, that would be the half dims in the local space of the ellipsoid. We then scale it and rotate it into view space using this lovely function. So it just takes the axis vectors, multiplies the half dims xyz, and effectively produces a maximum half extent inside the new space, which is view space in our in our case here. Center position is just the translation component of the matrix. No debugging to do with this anymore. We get rid of that. Get the near clip plane distance. Oh, I need to go back to that RTAA code. I want to get this one little line here. Well, all those lines actually. Oh, not tile. There we go. So I would like to get these boys and girls too. Nice. Right, so if we're behind the camera, don't bother trying to put this ellipsoid into anything, right? So that's another thing as well, is like if we're actually fully off of the screen, don't bother putting it. So when we scale it down, we should be careful, right? We should check if we're outside the bounds of the screen as well. Hey there, spherical cap. Are you using ellipsoids to do occlusion content? No. I'm using ellipsoids as the primary primitive to render. So rather than triangles, it's ellipsoids. So it's just an ellipsoid renderer. It's got PBR from shading, you know, just doing what games typically do these days there. But yeah, it's just I'm bending these ellipsoids into screen tiles and then rendering them. So I've done many different renderers in the past. This is just me redoing the most efficient one that I had. And we're going to be adding occlusion culling very soon because I had it in the past as well. Definitely a good tool. But yeah, I've not thought about doing occlusion culling with ellipsoids. But yeah, I guess you could use that as some kind of like basic primitive to render instead. I see. But yeah, we'll be doing some occlusion culling soonish. Hmm. Right, where we go? Where do we go now? So, yeah, I'm thinking about what happens if the box is off screen. Well, in view space, you have four positions. You could check all of them and make sure they're See, after the divide by Z, yeah, you don't know in view space because it's before the projection. Yeah, so I guess after this you can tell. After the divide by Z, you could tell. You could technically tell here. But yeah, so if you say, right, we'll just do it here. So we'll say if min max if all is it greater than? I think so. If the minimum point is greater than the graphics global, all right. Let me get these into some registers. Seem to be using it quite a bit. Makes it a little bit more readable, I guess, as well. Right, scene dims is kind of the screen dimensions, but whatever. Screen dims. Yeah. So if all of them are off the screen, the minimum point are off the screen, then it must mean or all of the maxes are less than 0. Technically it's less than or equal to, but it's float, so probably not going to get that. Yeah, that would then mean you're out of bounds. So outside the screen. Cool. You know, maybe maybe we can make some of this into a shared function for occlusion culling, but we'll just leave it like this for now. Yeah, essentially you want to get a view space. Probably make a couple of functions. It might be quite useful things. Yeah, let's make these into some functions. We probably want a function for going from just take an ABB and just get a screen bounding box for it. We probably also want another function which allows you to get I think that will be it. So I guess you could encode that as a min-max return a float 4, something like that. The issue you'll have though is yeah, it's all possible. Cool. The function you'll need is you want to return a vector 4. It will be something like transform ABB outer ABB to screen. Did you want to go the full way? Which includes doing the other one. screen from local, probably be the name. So it'll kind of be all of this. Um, so I want to take. Yeah, maybe you don't need to pass any of this in. This would be quite good. The issue is you need the screen dimensions, whatever that is. So this one needs to come in. Whatever your screen dims are. You might need some other camera stuff as well, to be honest. So what's the field of view? You might want to pass this in two separately. This could probably be part of some structure somewhere, like a camera. I don't know. Pull it from there or something. Right, if I remember, I had this as a bit of a different name, so that really won't compile. There we go. So, essentially what it's going to do is, if we just return 0 for everything, if there's a failure, because there's a check. Right, okay. Then if there's a success, we'll put the min. I think I've got a thing for this v2, is that right? Right, so min point screen space dot x dot y. Right, but we can swizzle that back out. That'd be cool. Nice. So we take this. It'd be pretty sweet. We'll take it and chuck it next to this one. So outer ABB. Screen from local. Oh shoot, we didn't pass in the transform. Transform 3D. What's happened with hands today? Right, view from local this time. This is kind of meant to be ambiguous. Right. Good. That'll be nice. So maybe we can make another one which sort of doesn't have this part of it, and it just does it from view space, but yeah. That's alright. Cool, so inside the shader, now instead what we have is this lovely function to call. We'll just call it R, I guess. We need to pass in that view from ellipsoid, followed by the screen dimensions and the clip plane distance. And then we can get out that sort of min, which would be r.xy, and then zw for the max. So we delete all this code here now, because it's all just in that lovely function, and voila. So we can then use those min and max points to then, what we need actually is the center position and half dims. yeah, you don't know what the user wants, I guess. So let's just do less operations because they might want min or max. But in our case, we just want, yeah. So how do we know if it was out of bounds? So we say if r.xy, so if all is equal, rxy rzw, then we know that we are out of bounds. We could set 1 to infinity, and that might just be so here we want to say either behind camera or out of screen bounds. Neat. So why don't we change those to infinity instead? That'll be better. Cool. Right, so after we've got that screen bounding box, we can now iterate over all the tiles and add sort keys into the array. So we could debug it. We'll leave this here. So what we're looking for specifically, maybe we could say, hey, draw the first one. That'd be interesting. Right, this just puts it onto some storage buffer somewhere, and later on in the frame it'll just draw whatever you've asked it to draw. Fire another shader, it just writes to the screen. Right, so I've done this code in the past. I think we have to sort of round down and round up these min-max coordinates. So really I think these can just go in the debug section, because what we actually need is the min-max. And yeah, I think that's it. So if we go to past version, where I think we hit iterate over all the tiles, I think if I had to search for tile bin again in this one. Yeah, this is it here. Yeah, there's the code. So we'll make it probably a bit nicer to read. What is this? Alright. What are we doing here? Well, we're dividing by some kind of tile dim. So in our graphics globals, graphics global. Yeah. So in our graphics globals, we upload from the CPU side some information, and some of the information that we need is actually the dimensions of the tiles. Now, I don't have any for UI. I thought I put them in here, but no, I think they're hard coded. Yeah, so we'll just dump them in here. So probably 32, we want like a tile dim and then a grid dim maybe. how big is a single tile and how big are the grid of tiles. So this will be the ellipsoid tile tile dim, tile grid dim. Like that. So we'll populate these. We should probably do that right now, because if we don't, I'll forget. And then we've just got junk in there and so we'll find where to make those. There's ones for some UI. UI. Right, it's this sort of code here. When do we know? Ah, here we go. So we actually know here. Oh, where's the tile size? Oh, okay, it's right here. Right, so we'll call it ellipsoid. Huh? Ellipsoid tile size. Let's just hardcode it to 16 for now. We should probably change it. Then tile. So for the scene, this would be, because the scene could be textures rendered to the screen, so it could be smaller. So that's the number of tiles that we'll need, and these are the grid dims. So that would be divide round up, yeah, then turn into a int. Then we just say x times y. Neat. So with that information passed up to the GPU, so we could probably store that in a little local here, just to not make it so it's just flying off the screen. So we could get rid of ellipsoid now, since this is the ellipsoid binner. No need to be as descriptive with the names. Convert to a signed int, because signed problems. Right, you could technically go off the screen, so we're just catching that bug, if that will be a bug. But we shouldn't do, because we do bail early. Hopefully. Neat. I pressed the wrong thing again. Right, then the top right is going to take... Alright, so bottom left is min. I could just call it min. Tile chord min. Tile chord max. Let's call it Right. So we divide round up. The max point, right, with dimension. Then clamp it. Neat. So let's divide round down, divide round up. Cool. So after that, this was me just trying to do some printing. Maybe we can debug draw though. That also might be useful. We could say, hey, this is the first sphere. Debug draw the tiles. Shouldn't be too hard to do that. Yeah, so iterate over the rows, then the columns. Yeah, technically does the columns first, then the row, but yeah. So it's getting the tile index, binning the tile index into the high bits of the sort key, then writing the sort keys out. So in our case, this is the ellipsoid index. We're binning that in there. We've got to make sure we calculate the depth though. I calculate its fixed point. In a previous one. And then we upped the number of tile. Why did we do that? Let's go back to the previous code and figure out what's going on. Figure out some of the context. Right, that doesn't matter for this anymore. So where do we get this depth thing? How did I do that? Closest depth, then pack using fixed point. Right. We don't have the closest depth thing anymore. Right, I want to do that. The information is all in this function now, which is a bit of a bugger, and we've kind of maxed out the number of things here, and I don't have other ways to... We could return a structure. That might be the way. But yes, the closest depth that comes from screen bounds and depth. Right. I pass muted this, obviously. And then that closest depth was... Right. I see the maths. Okay, that makes sense. Okay. Right, I'm just going to pop and get a drink. When we come back, we'll get this closest depth thing, because we do need that. Yeah. Could this create problems if it's wrong, though? Yeah, that's the issue, isn't it? Ideally, we want a closest point along the ray. Yeah. Um, yeah, we'll have a think about it. Or I'll be back in a couple of minutes. Alright, welcome back, folks. So, Yeah. Effectively, right, if we have a view thrust like this, we've got a couple of ellipsoids in the scene. We have a little screen tile that we're binning them into. Right, we've got a lovely little view ray. What we need to do is kind of just take the best guess. Like if it's wrong, the transparency will be sorted a little bit weird. Um, but yeah, we're just taking the best guess. So I think the way I did it is we just use that. Yeah, we take like the nearest point on the bounding box of the ellipsoid as the depth. So we are taking the bounding box, taking like the nearest point, and taking the z of that, and that will get us the depth along the ray that we're sort of just. It's not quite like this. I'm just drawing it probably because it's perfect, but yeah, it's going to be wrong. So yeah, it's kind of the best guess. It will kind of be a little bit in front. But yeah, I guess if you have an ellipsoid that's transparent, the reason why we put the depth in there is so they're sorted front to back. So if we have two ellipsoids which are transparent and they're kind of going through each other, or one which is opaque and the other one which is transparent, you might get some problems when they overlap. They might swap. But we'll see how bad that gets. Because it's an estimate, it actually depends on the dimensions of the ellipsoid and its position, because of the way the algorithm works. But that's that. So we've got to do something like this in this function. So what we actually want is something like 20 closest depth. All right. Einstein. What does that want? It wants the negative, negative. Oh, negative everything. Nice. So nearest point in view space. That's just a subtract then. Magic. Take the length of that. Yeah. Why take the length of that? Yeah, I don't like the idea of doing a length. So that'll do a length from there to the closest point. There's like the lower left near. Do a length of that. Versus just using the Z. Maybe, because this one's doing center position. It's doing because it's kind of offset from the ray. Center position take the half dim, so it kind of gets you that Z instead. Yeah. We probably don't care about. Wait a minute, what is this? That'd have been a dot Z. Why can't I just do that anyway? Because it's in view space. If the absolute of the center position is less than, it's kind of like near the middle of the screen, just use that. I don't see the problem with that. Just use the closest. If we just did this line anyway, I might make another function. No. Okay, so I think this might be it. Because it just needs to be some kind of rough guess. That saves the extra branch as well, which is great. Alright. Yeah, so I need to return some strut, right? It's kind of like a screen bounds. And depth. So it's got that min point screen space, max point screen space, and the depth. Kind of a rough depth. Yeah, whatever. So we'd say r dot depth infinity maybe. Now, all we're looking at doing is filling in r depth with closest depth and r with min point screen space and max point. And return r. Cool. So with this, now we've got a structure that gets returned. So it's a little bit different, but it's for the good of the code base. So we'll pull these ladies and gents out. Yeah, so now I've got this depth, right? So we go over all those tiles in screen space, and for every single tile that we encounter, we encode the tile index. Hang on a minute. We encode the tile index into the high bits, and then we encode a fixed point representation of the depth. Now, I need to actually calculate that. I think I have this function in this code base. I think I carried it over. Yeah, I do. It's a little macro that I use to just basically pack and unpack fixed point numbers with whatever yeah, combination I like. So that's not 10-8. What are you talking about? Fraction bits. that'd be 8, 8, wouldn't it? Let's write a thing for that. So 8 integer bits, 8 fractional bits. So why am I ANDing it? Yeah, why am I ANDing it? Huh? Yeah, I think this whole code had a bug, to be honest. So I'm trying to fit it into set number of bits. So the higher bits takes the gotta be really careful. Yeah, so 18 bits goes to depth, to our 18-bit depth. We probably can get away with 16-bit depth. So, you know, we're not going to have a far of 256, but this has a far of 256 because we've done 8 integer bits and 8 fractional bits. So, you know, you'd have 1 divided over 256. That's kind of like the smallest unit it will step by, right? And it says 256 to get to a full 1. Those. Then you've got 256 integer bits, right? So when I oh, wait a minute, I know what it's doing. Sorry, I was confused. It's packing it. All right. All right. I don't know why I'm saying. Right, when I'm saying 10.6, what it's saying is it won't be setting any of the higher bits, probably. Maybe we should AND it. Yeah, what we should probably do is when you pack, this is a 16-bit number, right? We'll be doing like a that. Right. Just to illustrate that it's only a 16-bit number, but really this supports up to 32 bits. It's just we're not encoding enough data in there for it to overflow. And if we did, it would mask it, right? So really what we want is something like this as well for this one. And that makes it a little bit clearer what's going on. Yeah, this is a 16-bit value. So I don't need to AND it. Right, so we pack it down. Crap, did I just do it the wrong way around? Right, so packing it down into flow returns an int. Into a fixed point, it returns an int. Then unpacking takes in a float and return Sorry, takes in returns a float. Cool. Right. So we pack it down, no longer needing to do the add. That's just inherently a float 16, so there we go. That'll work. So we're in the higher bits, we're packing 16 bits. So we had a 4K screen with 16, so a squared 4K screen, 4K by 4K, 16 tiles per, sorry, 16 pixels per tile along each dimension, 256 squared. Perfect. So that will mean that fits perfectly into 16 bits. So that will not overflow the sort key. It'll become a problem though if you just increase the resolution past that. So we'll need a way to dynamically handle that tile dim. Yeah, we could look into that. The dimensions of a tile. Right. Okay, so how do we... So I guess this is quite problematic now. I think typically you want 64. Right. So there's one more problem with the shader. Oh, that's right. You have to atomically... So we'll need some kind of way to bulk... Yeah, this is not good. Right. Yeah, for now we're just gonna do this. Oh, we can't do it like that. There's multiple ellipsoids. The same ellipsoid gets put into the different tiles multiple times, right? So we need to add some system memory start. Good. So I want to put in something where it's like ellipsoid sort entry next index. So the start of a frame is a shader called frame start. Allows us to set up some global sort of context. Just set up stuff. So we just clear it to 0. Then what we can do is in that tile bin, we can atomically, so we get the number of tiles we're gonna actually go over. Right, we kind of messed that one up a bit. No biggie. Min max. So we want to get that sort of like sort entries start index. Or we say sort entry. I call it insert index. And you're going to increment 1 by the insert index here. It needs to become insert index. And then where we'll get is we'll do an atomic add. Now, this will typically be a bad thing to do, but we're going to be incrementing multiple. So it shouldn't be that bad. We're not doing it for every single time we insert a tile entry. We're doing it once for every single ellipsoid. So it's a bit better than the more naive approach. So again, the number of tiles, basically, and atomically adding. This will return us the insert index, because it returns us what the value was before the value was added on. We can then do And just subtract then a multiply. So product elements S32 times 2. Then you'd like to do a subtract between the max and the min. And then you take a product between the xy. So yeah, multiply the xy after the subtract. And voila. Neat. Pretty cool. So I guess we could put an if statement here for say tiles. Right, just in case. Just in case it doesn't go over any tiles, it should always go over a tile. And I think it always should. Save the check. Right. The final thing we'll do in this shader is figure out, does it work? So we want to debug draw the tiles. We've got some code here already, which debug draws a box in the screen for the first ellipsoid. So inside this loop, we'll do the same thing. So we need to get, we could probably do it with a min-max. So we take the tile coordinate xy. Yeah. So we can do like a, so I reckon, right, we can do a tile x multiplied by tile dim, right? That will get us the screen position. Yep. I want to do the same thing for the y. Now, the reason why I wrote it like this is because I wanted to. Oh. Oh, what am I doing? Wrap it, add 1. So we add 1, that will get us the max coordinate. Right, so, and then multiply with the tile dim. Cool. We can then use those to, I think there's a min-max. Yeah, I don't know why I didn't use it for the other one down here, but oh well. So, mn, mx. Neat. So we use a depth which is further away than this one, so it goes behind it. We'll have an infinite border. Or, alright, we have a bit of a smaller border. Let's do 2 pixels instead of 4. Okay. That should be fine. Cool, so I guess let's go ahead and, you know, maybe we should get a nice color here for this. I don't know, what am I throwing here? We should probably have a nice... Yeah, I don't have a hashing function. We should probably get one. Well, for now, we'll just do something a bit dodgy. Just awesome bits together and just roll with that, I think. Yeah, so hopefully get a bit of a different color there. Cool. Wait, doesn't that nice color do it? Oh yeah, the nice color already does it. It's around we get the hue, doesn't it? Yeah, we could probably have a better hash function. Right, so we should be able to just pass in the tile index. That ought to be good enough. Right. So, this is where the fun begins. Let's test out the shader now. So we don't really have a... We're not rendering these yet, but we're definitely going to be giving it a nice good run. So RTAA. So we'll pop in here. I think we'll copy this here, and we'll all right. Tile bin ellipsoids. We've got to sort out our inputs. Ellipsoids count. Right, maybe we'll put it as part of this thing. We can get the count. Count divided by, I think I did 64, wasn't it? I don't know. We're a bit careful, we should probably make it 32. Local group size. And then 111. Alright. Right, so the inputs are actually the ellipsoids buffer. So we are read only on that currently. So bin ellipsoids buffer. Then we have the sort keys that we're writing to. Good. And the sort payload. Damn it. I've got the plural. It's going so well. So yeah, we're just gonna go ahead and sort keys and oh, I forgot to plural the other one as well. Horrendous. All right, so that's gonna launch the shader and hopefully run. And to verify it works, we're gonna debug, visualize what's going on with those drawings for the first ellipsoid that we bin. All right, see how well that goes. Here we go. Right, so something wrong with the syntax here in the shader. I don't know which part though. Where is it? I see it. Probably a handful of these. Don't worry. Or shared. Right. Here's me like, yeah, just making up my own language apparently. Is not implicitly type 2 matrix 3D. Why am I doing that? You want a matrix? Oh yeah, you need it to be a matrix. Yes, you do. Right, so this one's not a matrix, it's a transform. So this guy's scale, translation, and rotation is separate variables. So we need to translate that over into a proper matrix. Now, Yeah. Yeah, I wonder about all this extra maths. Gotta be careful. Alright, let's keep going. So this one is, I forgot to say .z in the here. It's a shame Visual Studio cannot read my compiler. No, Clang has to change the way it does its line hit things here as well. I just can't be bothered to do it. Right, why is that a float? I see. Scalar version. Is that redeclaration of R? It is. Isinf, right, it's not a function, it's isinf 32. Nearly there. Times 2, please. It's just called grid dims instead. Atomic add U32. Things are looking a bit more promising. Right. Seems I've got to the proper Clang compiler now. Not my shader compiler. So we're going... Right. I did a bit of a rename, but didn't rename the definition. Fingers crossed. And... Right. We're running the game. What? I'm running the shader apparently. Here it is. But I cannot see anything happening on the screen, which sucks. So gotta figure out... Oh, we didn't set the count, did we? So it's been zeroed. Yeah, so we go to tile bin. I didn't set, there's another field called ellipsoids count. And that, so none of the code was actually running in the shader. It's fine. Let's give it a nice run. Right. Oh, progress. That was a bit buggy though. As in like, why was the performance that bad? Right, what was bad was the draw 2D stuff. Apparently the draw 2D render cannot simply handle that many shapes. Which is a damn shame. Man. I don't... So those draw 2D and draw 3D debug stuff I've got, they go per pixel, they go over every single shape. They're not optimized like these things that we're writing here. We should probably write a tile binning thing for those so we can handle a high number of shapes, but it's the way it goes. So yeah, it can't handle like, you know, less than 64,000 shapes. So, which is a bit of a problem. It's like, what's going on? Anyway, let's just visualize it and hopefully the stream doesn't choke. So yeah, if the it's got a bit of a bug where it was at 0, 0. But yeah, it's kind of working right. You see the lovely colors. So the white is the screen bounding box, and the sort of different colored tiles are obviously the tiles, and they're only rendering the border so we can see the ellipsoid. Um, so this ellipsoid is being inserted this many times in, well, a sort key and and an ellipsoid index is being inserted into that array this many times. Yeah. Obviously, the bigger the ellipsoid is, the more expensive this kind of loop is going to be. Maybe there's ways to optimize the big ellipsoids. You could probably put them into a different buffer somewhere and say, do this later. And it could. But I don't think we're going to have that problem too much. Yeah. So that seems alright, doesn't it? So now this would have filled. Yeah, so the one problem with it that we saw is if the ellipsoid is at 0, 0, 0, it doesn't work. But that should never happen, but we should probably handle that case. But yeah, we go to the edge of the screen, see it starts lagging now because it's trying to bin or draw a ton of those. Yeah. And we've got such a high field of view that it's going to be excessive. Right, shouldn't be doing that. We should catch that bug. We'll catch those two bugs and handle them gracefully. So let's not draw the tiles. Let's just draw the screen bounds and see what's going on there. So one of the bugs is like if the center position is at 0 in view space, it's doing something. Oh yeah. See, it's this stupid sine function. Like, so basically, the intrinsic sine function, and I should probably like not use this. So I use the intrinsic, which is built into GLSL standard library. But I should probably just be like, screw it, it's a stupid idea. If it's exactly 0, it puts 0 in there. Right, which is not technically what sine means. Right, a sine, 0 is technically positive. Sine. So, and I don't know if there's a case where you want this. There might be a case, but typically the case that you want is you just want it to give you either -1 or 1 and to be decisive about it. So that's returning 0, then I'm multiplying by it, and yeah. 0 F32. Heck yeah, how's it going? Yeah, it's give me 0 F32. Oh, nice. How you been, sir? So, I think, right, we should just be like, screw. I should remove this from HCC as an intrinsic. Or at least just do a select instruction. Because it's just so silly. And then we won't have problems like this. I think that'd be ideal. Or because the problem is like it's more than just a copy sign uses it. Yeah, whoever did this probably made a very big mistake. But yeah, I shouldn't have to do that. I shouldn't be copying that same mistake. Problem is I've got to change my compiler. Not hard to do that though. So we're changing my compiler quick. We'll bring over the changes. And then we can so I'll open up this folder in Visual Studio. We'll look for what is there? It's called like sign underscore, I think. So why is this in game without an engine? Oh, because it's down hard coded to the right. So there's nothing, that's just the header files. We will have to change in this header folder because this is actually an implementation for CPU side. So it's been nice and easy just to get rid of this stupid design. Right, if it's actually less than 0, -1 if not 1. Right. Yeah, I can't believe I copied that stupid design. Cool. Then inside the shader compiler, it will detect the name, sign, whatever, and then actually emit that silly GLSL sign. Crap. That sort of stuff. Oh, maybe I didn't do that. And if I didn't do that, can't see it. Be in HTC.h, wouldn't it? Function many. Yeah, it's right here. Alright, this one. So, sign. ML sign up. Then go down to the lowering into Spear V. Alright. So we've got to do our own. Yeah, it maps it into this stupid thing here. So we nuke these from there like that. We'll just write a specialized. So we just need to write a select statement. So select is like a ternary operator, right? So yeah, gotta work it out. So where's the Boolean? You can have subcases in a switch. No. No. You just put another switch inside a switch. That's all I'm doing. So I've filtered it to these two, and then yeah, all it is. Where's the Boolean operand? Yeah, this is it, and it was that. Add instruction in the combine op. Yeah, it's this sort of code I need. Need to figure out what the combine op was. Right, spv op. Sweet. So I just need to do like a less than or something. Right. So this is basically the code I want. Submitting some spv instructions. So all we want to do is you've got x, which is your value. If x is less than 0, return -1. If not, return 1. That's all we're writing here, just in instructions. So if we do spv op less than, just got to find it. This, yeah, okay, so we've got to actually select two different ones. So depending on the type. So type class of the data type. So we'll figure out that. So operand 0 will be the return, 1 will be the first argument. We only have one argument, so that'll be it. Get the data type, get the type class. And we can use the type class to know what operation to use. So we could probably say type class equal type class float. Then we want to use, well, okay, let's just call it the compare op. HCC spivvy op compare op. So if it's a float, figure out the floating point 1. If not, we use the signed int 1 because they're the only two options. F unordered less than. Neat. So we need a couple of things in here. So we could you want to say if operand, we've got to convert the operand as well. How do we do that? Convert operand, that's it. So the first operand, so will be this here. Yeah, so we're writing this expression right now. So there'll be 1 in there. Oh wait. We need to make a new temporary one. This is the so ID. Condition result ID. We just allocate your spivvy ID, drop it in there, and that's the return. Then this X is convert spivvy ID. We convert my abstract machine language ID to spivvy1. That'll be that X. Then we need to make some constant of 0. Depending on the type. So I think you say constant deduplicate 0. This is it. Oh, the code was below. Great. So we do this constant uh, 0 for whatever the data type is. That data type is like that. Cool. Nice. Now the return data type, I don't really care about that. Nice. It's already got up here. So we then get the storage class for do the select instruction, which is the ternary operator part. If this result is true, return the first one. Should be -1. I think I've got -1. Where the hell am I? Yeah, luckily past me has done a -1. So I want a -1 or a 1 for that data type. Nice. That that should be it. It's going to return the return value ID. So actually there's a return ID, and that's what this is. Here's a return ID. Cool. That should be the compiler changes to fix that 0 bug. So if we recompile and run, so I think it's scripts build. Right, what is this? Let's build a new version of the compiler. Should build the samples as well. CD to samples. Actually, we'll just go over there and see what's up. I think it changed. So if we go to samples, yeah, it changed today. So yeah, that's good. So we double click it. There you go. It's running the sample now. So they seem to be working all right, I think. I forget where the sign is being used. We'll go over all the samples, just double check. Just in a bunch of different texture reads this sample. It's got about 10 of them. There we go. Well, it's going to be more than 10 apparently. This sort of alternative color picker, which is not really a practical color picker, but it looks cool. My SDF ray tracer, which apparently has a bug in it. Maybe it's just because it's 4K and the step distance is terrible. Or it's not stepping properly. Here's the HC logo voxelized into 3D. Just extruded along with third dimension and ray traced as a voxel texture. SDF example. And then back to the triangles. Right. Good. Seems alright. So we're going to run the release build so we get an optimized compiler build. And then we'll just drag those files into the project again. So when we get back to Linux, I'll need to do this again. But for now it'll be the other way around. The Windows build will work, but the Linux build will be broken. But yeah, I'm hoping to get that sorted out soonish. I need to order a new drive. So Windows EXE. Well, okay, it won't be broken. I have a slight bug. We're fixing a certain bug doing this. Then we want to hmaths. Ooh. Means I make 2 commits because it's a submodule, isn't it? scalar. Was that it? Because vector doesn't have anything, isn't that right? Vector. It just calls, yeah, it calls the scalar one. Nice. Cool, so we can just close that Visual Studio now. And boot up. Here we go. So hopefully this works. Let's run the game without an engine. Now I'm not going to touch the mouse, and if the bug... shoot. Well, broke the compiler. To do source core I think that's got the wrong file. I don't know. Anyway, spivgen 1615. Don't understand. Yeah, those are all messed up, those line numbers. I could try and run... It must be something to do with this code. We did remove... Those numbers all seem alright to me. There's only two types of sine functions. Cannot see... where it is, unfortunately. Maybe we'll have to hop in the debugger and all... Did I set this up in the past? I must have done, right? So... yeah, I forgot how I used to debug exe. Oh yeah, you can open up the exe in the debugger. Yeah. Right, what you can do is go to build. Right, the build folder's not showing up for some reason. And you can say set start item. And we want to change maybe you do this. Interesting. Alright, see what happens. Oh, what was this? Let's see if it goes in. Well, I think if you press F11, it will pause on. Yeah, good, good, good. So, what is argv? Cool, that worked. So all I have to do is point it towards the. All I have to do is go into HCs. Well, game engine, and I need to open up the build.bat, and I need to nick all of these lovelies and dump that into that JSON file. Right, I've got to comma separate all of this. Oh, they do it all automatically. Neat. What's all that? Right, dot game without engine. I think that's it. Right, let's try relaunching that and hopefully it will crash. At the bug, right. Right, I think we need an extra dot dot. Because it's in the build directory. Don't think I care about the metadata, to be honest. Neat. We hit it. Oh, it's the -1 table. Alright. Right. Oh, so even vectors are going into here? Right, I didn't handle the vectors. Whoops. Let me do that quick. Right, so the problem is the if it's a vector basically, get the number of fields. Oh. Get the scalar data type from a signed in. Yeah, how does this work if it's a float? Right, I do the conversion. Good. -1, -1. Right, I didn't realize that wasn't implemented. So if we run the build again. That should be the fix. I ran the release build and it packaged things. Right. Expected. Yeah. So we need to do a special boolean in the Spivy code gen. We need to select the right boolean vector type. Plus columns. Let's look for that. How many columns in the base data type? Cool. And the select instruction will work with a vector. Nice. So we'll quickly compile it. It's not release build. Be a bit quicker. Compiles a bunch of sample applications as well. Cool. So apparently that ran successfully. Now let's go actually bring it over to the game again. We'll get this all ready. Just the executable. Right, seems like that's compiled. Right, and let's run the game. Okay, so I'm not going to touch the mouse. So if the border shows up around the ellipsoid, then the bug is fixed. Yeah. That's what we wanted to do. So the bug was the sine function checks if the value that you want the sine of is 0, and if it's 0, it would return 0. But we want it to return 1. So we've just changed the compiler to do that behavior because by default in shaders, other shading languages were just copied. Return 0 on 0, and it's a bit silly to be honest. So we've just corrected this mistake in our compiler. And it works with vectors as well, which is great. So we can, yeah, mark that one off the list. It's good. Right, there was still one more bug, wasn't it? And I guess I'll write it down quick. Yeah, the bug was if you move the screen down on it. Yeah. Right, so if you go perpendicular to the... Yeah. That's real bad. Interesting. Right, we'll solve that one next time. We'll start here next time. So that is look directly down or up, and the screen bounds box stretches. Ooh. So we want to fix that bug before we move on to actually accepting these sorting the list and then ray tracing against this list. But yeah, we're a few things, a couple things to do. Cool. Alright, so some good progress today. At least we got the binning working. Awesome, and we fixed a compiler design. That was cool. Right, so we'll next be on Thursday. About 4 hours ago on Thursday. Sorry, 3 hours ago on Thursday. And then 4 hours ago on Sunday. Right, so in the meantime, if you want to come and chill and hang out, there's a Discord. Talk programming and things. When am I taking a break? Christmas. There'll be some kind of break. I might not be streaming on Boxing Day. Something like that. But I'll keep going probably. Maybe Christmas Eve as well. So it might be these 2 days around Christmas. We'll see. But I might, just depends what's going on. I'm definitely busy on Boxing Day. We'll see. Who's available to raid? Raid TCAP. Right. I hope you guys have a good evening. Have a good tomorrow. And hopefully see you all Thursday. Thank you for popping by.